Welcome to 1D Kinematics. Today we're going to be going over position time graphs. One of the great things about science is graphs kind of tell the story of what's going on in a lab, in an experiment, or just with concepts. So in math classes, you've examined graphs and determined information about different patterns. You've also taken patterns and graphed them. We're going to do the same here today. Change over to a different thing. The easiest graph to analyze that we're going to start with is called a position time graph. Now notice that it says position first and time. When we were going over the lessons earlier, we had position, right? Like a position 1 and position 2 relative to a reference point. Okay, so when it says position, it's referring to that, and then time. And so if we were to graph this, and we graph it like a, then we would have an X and a Y axis, and a Y axis. So the first word, position, is the thing that always goes on the Y axis. So here on the Y axis, this is going to be giving position. And here on the x-axis is going to be giving time. So when we say we're going to analyze position time graph, this is how we're going to set up our graph. There's a few components that are needed in a graph. You always need a title. You always need to label the axes. And you always need to include units. So for position, what would our units be for position? If you're using SI units, most likely it would be meters. And for time, most likely you'd be using seconds for time. Okay. That's the same slide. Okay, so here, consider the simple graph, position versus time for walking to school. So here we have position in meters, and this position, is that a scalar or a vector? That is a vector. So notice that we have the direction in brackets, south. So position is in meters and direction is south. And then on the x-axis, we have time in seconds. And here we have the title. So it has all the necessary components, position versus time for walking to school. So examine the graph to answer the questions that follow. Where does the student start walking from? Where is the student walking to? And how far is the student's home from school? Pause the video and answer those questions. So where does the student start? Let's see. Where does the student start walking from? He's walking from home, which is position 0, right? And so here, if we look at this, we have the position, and it's a vector, so it has the vector hat on it, and the position is 0 meters. Now, keep in mind that even though this is a vector, because the magnitude is 0, we do not have a direction. Okay, any other thing, any positive or negative number would have a direction associated with it. And where is the student walking to? He's walking to school. And that would be at position 80 meters, because you can see that the destination is at the very top of the graph. And so here he starts here, and he's going to end here at school. How far is the student's home from school? It would be 80 meters south. Okay. How long does it take the student to walk to school? How far has the student walked after 30 seconds? And how long did it take the student to walk 20 meters? Pause the video and answer those questions. Okay, so here, how long does it take for the student to walk to school? Well, the school, we already said, is 80 meters. So that would be at this point. And so how long did that take? That took 60 seconds. How far has the student walked after 30 seconds? So that would be here. So we can look at this and we can draw. 30 seconds would go to here. And how far is that? That's at 40 meters south. Okay. And then how long did it take the student to walk? 20 meters. So 20 meters, here's 15 and here's 30. So this would be kind of like 20-ish, and this would be kind of like 25, and then there's 30. So 15 is going to be somewhere, excuse me, Oh, excuse me, I did that wrong. It wasn't asking after 20 seconds, it was asking how long did it take to, so 20 meters. So 20 meters is right here. We can draw a line here, and then we can go down and see what the time was. And how long did it take the student to walk 20 meters? It was about 15 seconds. All the previous information can be read from the graph. Reading the information from a position time graph provides information about the position and also how long it took to get to those positions. Now, if we find the slope of the graph, remember when you're trying to find the slope of a line with a straight line, that the slope is rise over run. That's right here. And what is the rise? It's going from 0 to 80, right? So the rise is 80 meters, as shown here. And then what's the run? The run is going from 0 to 60 seconds. So the run would be 60 seconds. Now include the units. So we have 80 meters south and over 60 seconds. So if we multiply that out, we get the slope of this line is 1.3 meters per second south. Does this look, now if we look at the units of this, if we look at those units, we have meters per second and we have a direction, right? South. Does that ring a bell? Considering the units, what information does the slope of the position time graph provide? What do you think that looks like? The units of the slope are meters per second with a direction. The slope's units match the units for velocity. Remember the velocity? So the slope of this position time graph gives velocity. Here we can recap that. Here we have rise over run. And what we get is position 2. The rise is position 2 minus position 1 over time 2 minus time 1, right? Because if we look at here, this would be position 1, and this would be position 2, and this would be time 1, and this would be time 2. So the rise would be position 2 minus position 1 over time 2 minus time 1. That would be the slope. And so we could rewrite that because we know that when you do a change in position, you can use the delta D means D2 minus D1, and the delta T means T2 minus T1. And that's identical to the equation we came up with for average velocity. VAV is equal to this. Those are identical. So we know that the slope of a position time graph gives you the average velocity. Okay, through comparing graphs on the same scale, we can learn more about what the shape of a graph tells us. So here's a scenario. You have 3 siblings, and they walk to the same school 300 meters east from the same home, but they don't walk together. They walk separately. And so rank which sibling you think is the fastest and slowest based off of the following graphs that we're going to show. Then calculate the slope to determine the average velocities. So first we have Alfie. Alfie walks to the school, which is 300 meters east of his home. And you can see that Beth, she does the same thing. She walks to the school that's 300 meters east from her home, and so does Cameron. So you can see they all travel the same distance. But now let's look at their time. So here you can see that the slope of this line, he goes 300 meters in how much time? In 240 seconds. So our rise is 300 meters east, and our run is 240 seconds. So if we find the slope of that line, and we calculate that out, it's going to be 1.25 meters east per second. So that's the average velocity of Alfie as he walks to school. Beth, she's booking it. She does it in 120 seconds. You can see that the slope of this line is steeper than the slope for Alfie. If we put that in here, 300 meters over 120 seconds, we get 2.5 meters per second east. So that 2.5 is twice as fast as 1.25 meters per second. Now let's compare it to Cameron. Cameron makes the journey in 180 seconds. So this is kind of like Goldilocks and the Three Bears. Just right, in between. So Cameron does it in 300 meters and 180 seconds. And if you multiply that, that's 1.6 meters per second east. So you can see that from the three students, we have Alfie is the slowest, Beth is the fastest, and Cameron is in the middle. Summarize how the slope of the line on a position time graph relates to an object's velocity. So you probably noticed in the example that a steeper slope indicates a faster velocity. So here we go. Here's another example. And notice, if you look at the title, you always know what's going on. It's a position versus time for walking to school. So here's our position, because this comes first, right? And here's our time. And you can see that we have, it changes. So it starts out looking like that. And then it changes. And then it changes, the slope changes again. And last but not least, the slope changes another time. So describe the student's motion. So the student walks at a steady pace, right, for about 40 meters. Then the student stops. That's this stopping. So they're staying at 40 meters. That means for, I don't know how long this is, but about 7 or 8 seconds, the student is stopped. Then the student moves at a quicker, see how this is a little bit steeper? The student moves at a quicker pace for a short time, and then slows down and stays at a steady pace until he gets to the 80-meter mark. And here, notice here, now we're going west, not east. During what time interval is the student moving the fastest? Pause the video. Yep, right there. Right here. So it's between, if you look at it closely, we can say it's between here and here. And you can see that this is 30 and this is 45. So there's 1, 2, 3, 4 divisions between 30 and 45. So 45 minus 30, there's 15 seconds, obviously, between 30 and 45. But there's 1, 2, 3, 4 boxes. So if we take 15 divided by 4, that's going to give us the how much time for each of those boxes. So that's 3.75 per box. So this right here would be 33.75. This one here would be 37.5 seconds. Determine the student's average velocity in that time interval. Okay, so for the average velocity, we need the rise. It's starting at position 40, and it's going to position 50. So here, we've got our 50 meters west, because we always do D2, minus D1 over the time interval. 37.5 is time 2, and 33.75 is time 1, from here to here. So if we do the math, we end up getting 2.6 meters per second west. What is the meaning of the horizontal line? Prove it by determining the slope in that section. So here we have the horizontal line. What is the meaning of that? Pause the video and see if you can come up with the answer. Okay, the horizontal line means the person was stopped. The position did not change. They stayed at 40 meters the whole time. And we can prove that because the rise is 40 meters west. Is at this point, they're at 40 meters west. And at this point, they're at 40 meters west. So we have 40 meters west minus 40 meters west divided by, and the time interval here, it goes from here to here. Oopsie. Here to here. So remember, this is 33.75. And then this is going to be 22.5. So here we have that. do the math, and you can see, well, obviously we didn't even need the time because 40 minus 40 is 0. How does the student's average velocity for the entire walk to school compare with the first student's average velocity? Pause your video and then try to solve this. Okay, so both students walked the same distance in 60 seconds. The magnitudes are the same, even though the second student changed velocity throughout. The directions are different. So see here, this was the original student. And then here, this is the one we're comparing. We're comparing this one and this one. So here, this student, let me change colors, traveled 80 meters west in 60 seconds. And this student traveled 80 meters south in 60 seconds. So they're both going at the same magnitude, but not necessarily the same direction. Now, it doesn't matter. Like, a student could, go all different paces and everything. And as long as they ended up at the same position on the same amount of time, the average velocity would be the same. So a student could go like really, really fast and then really, really slow. See? Something happened where my pen isn't working. Alrighty. And it would end up being the same. Okay. So both students walked the same distance. The magnitudes are the same, even though the second student changed velocity throughout. Directions are different. Examine the position time graph for track practice. So here we have, I think my pencil is just dead, so I have to disconnect this to use my finger. Here we have another graph. Again, we have the position versus time for track practice. So here we have our position. They're going north, and here we have the time. Describe the motion. Okay, I'm going to pause the video and then keep going. So you can see that the runner is running. Then he stops, and then he keeps running, and then stops, and then runs, and then stops. And now he's all the way at 75 meters, right? North from the original position. And now he starts running back to the original position. And it takes him, a little bit more than 10 seconds to get all the way back. So what is the runner doing in the sections with horizontal lines? I think you know this already. The runner is stopped during the sections with the horizontal lines because there's no slope there. The velocity is 0. So that just shows that the runner is stopped. Find the average velocity of the runner in the last section. What does the sign mean? So in the last section, started at 75 and ended up at 0, right? So position 2 would be 0 meters north, and position 1 would be 75 meters north. And then the time 2 would be 40 seconds, and the time 1 would be 27.5 seconds. So if we do that math, we have 0 minus 75 meters over 40 minus 27.5. So we get a negative number, negative 6 meters per second north. And the negative sign means that indicates that the direction is opposite. So since the position is saying is north, if you get a negative sign, then that's going to just mean that instead of going north, that the student is going south. So the runner's velocity is 6 meters per second south. What is the runner's final position and overall displacement? So the final position is 0, right? This is where they end up. And so what is the position, which is D, right here, is 0 meters. And the displacement, remember the display is the delta D, is 0. Because it starts at 0 and it ends at 0, then the displacement will be 0. So here's some summary, some key terms. Position time graph, you might want to add that to your vocabulary list. It shows the position of an object as a function of time. A reference point, and we referred to this a little bit the other day, on a graph, it means the horizontal axis. And the slope of the graph gives you, for a position time graph, the slope gives you a velocity. That's not always the case. So if we're graphing something other than a position time graph, it might mean something different. And then it's got you the equations that we talked about. Just the main new one is that the slope is equivalent to VF for a position. These are all referencing position time graphs. Describe how the slope of a position time graph relates to the object's average velocity. Include horizontal lines and lines with negative slope. So here, what does this mean? This means the object is stopped. The slope is 0 and the velocity is 0. Position does not change over time. You can see here that they didn't write out position, they just showed you with the symbol, and that's fine too. You can just put the symbols in. Line with a positive slope. Moving with a constant velocity in the positive direction. That means that the velocity is greater than 0. The larger the slope, the steeper the line. The faster the object is moving. And notice here it's starting at the reference point, right? Now here you can see that they didn't start at the reference point. They started at a different location, and they started working their way towards the reference point. And you can see that it's a negative slope, okay? Which means that it's going in the negative direction. It means the steeper the graphs, the larger the magnitudes for the slope. They indicate that the object is moving faster. And that is the end of our position time graph lesson. It was a long one.